So this is the second session on friction. This is in continuation of the first video. In case you are new to this topic of friction, you must definitely watch the first video and then you must come to the second video. Okay. So in this video also I'll take up a theoretical discussion on friction. Okay. This will be in continuation of the first video. Okay. So in this also I'll take up a theoretical discussion on chapter on friction. So now first we'll talk of static friction. Okay. Static friction will be denoted by the symbol Fs. Okay. Fs means static friction. S is the subscript. Okay, fine. Now how do we define static friction? Static friction means force of friction between two solid bodies in mutual contact and there is no relative slip taking place at the contact points. This is called the static friction. Okay. So force of friction existing between two solid bodies in mutual contact and no relative slip taking place at the contact point. This is called the static friction. Okay. For example, suppose this is one body, this is another body, solid body B1, solid body B2. This is the contact surface, tangent plane at the contact point. This is the common normal at the contact point. Now these two solid bodies are in mutual contact and there is no relative slip taking place at the contact points. Then the force of friction existing between these two bodies is called the static friction. Okay, fine. Now, just as there is a law for kinetic friction, there is also a similar law for static friction. Let N be the mutual normal contact force between the two bodies. Okay, N is the normal contact force between these two bodies B1 and B2. Fine. Now, what is the law of static friction? Law of static friction is this. Law of is this. Let Fs denote the magnitude of static friction. That is less than equal to mu Sn and more than equal to 0. Okay. This is the law of static friction. Fs is the magnitude of static friction force between these two bodies in contact. Us is the coefficient of static friction between the given pair of surfaces. So μs is called the coefficient of static friction. Coefficient of static friction between the two solid bodies. N is the normal reaction between these two bodies. N is the normal reaction, and this quantity mu Sn is called the force of limiting friction. Force of limiting friction between these two bodies. Force of limiting friction sometimes we will denote this by F max. Sometimes we will also call it as the supply. Sometimes we will also call it as the availability. Various names. Various names. Mus is the coefficient of static friction between the given pair of surfaces in contact. Okay. I'll rub this one. Also, one more thing should be noted. For a given pair of surfaces in contact, for a given pair of surfaces in contact, mu s is more than mu k. Okay. This can be explained on the basis of atomic view of friction. This I'll do in the next video. Here I'm just stating. Okay. And one more thing, but what happens sometimes, what happens that in numericals, mu k is very slightly less than mu s. For example, suppose in some numerical it will be given that mu s is equal to say 0.6 and mu k is say 0.59. Since they differ by small amount, so what happens is sometimes many numericals we are told that the mu s and mu k are equal and they will be termed simply as the coefficient of friction. Okay. Many times it happens in numericals like that. In many problems, mu k and mu s are taken to be equal. Okay. And then we'll simply, suppose for example, we'll say that mu s and coefficient of friction is 0.6. Then will mean that mu k and mu s are both 0.6. Alright. So this point should be noted down. Alright. Now one more thing. What does this inequality mean? Fs is less than or equal to mu sn more than 0. This inequality means that static friction is a self-adjusting force. This means that static friction Fs is a self-adjusting force. It is a self-adjusting force. Fs is a self-adjusting force. And tendency of objective of static friction is always to oppose the tendency for relative slip between the two bodies. Samjha? Is it clear? Tendency of static friction is always to oppose the tendency for relative slip between the two bodies. Okay. And in order to oppose the tendency for relative slip, static friction can assume any value between 0 to mu sn. This is the meaning of the word self-adjusting force. When we say that static friction is a self-adjusting force, we mean to say that in order to prevent relative slip between the two bodies in contact, static friction can assume any value between 0 to mu sn. Okay. So this is what is meant by saying that static friction is a self-adjusting force. Okay. I'll rub this one, okay. So this means the static friction is a self-adjusting force. Alright, fine. And aim of static friction is always to oppose the tendency for relative slip between the two bodies. Okay. Now, one more thing should be noted down. That what I am saying is this. That suppose two solid bodies are in mutual contact, B1 and B2. Okay. Two solid bodies B1 and B2 are in mutual contact. This is the common tangent plane at the contact point. This is the common normal at the contact point. Now, there is no relative slip taking place between the two bodies in contact. Okay. Then it is not necessary that static friction will definitely act between these two bodies. This is in contrast to kinetic friction. In kinetic friction, whenever there is relative slip taking place between two bodies in contact, then kinetic friction definitely acts. Is it clear what I am saying? In case of kinetic friction, whenever two solid bodies B1 and B2 are in mutual contact and there is relative slip taking place at the contact point, this kinetic friction will definitely act between these two bodies in a direction so as to oppose the actual relative slip between the two bodies. But in case of static friction, if two solid bodies B1 and B2 are in mutual contact and there is no relative slip taking place at the contact point, then it is not necessary that B1 and B2 will definitely exert static friction on each other. Okay, it may exert, it may not exert. Okay. So one more thing I'd like to say before going ahead, that is a static friction force between two bodies obeys the Newton's third law. That is, if B2 exerts static friction force Fs on B1 in leftward direction, by Newton's third law, B1 will exert static friction force on B2 in rightward direction, just opposite direction. Third law is valid for static friction also. Okay. So now what I'm saying is, just now, as I've said just now, if B1 and B2 are in mutual contact and there is no relative slip taking place at the contact point, then it is not necessary that the two bodies will definitely exert static friction on each other. They may exert, they may not exert. They may exert static friction on each other, they may not exert static friction on each other. Now, how to decide whether they will exert static friction on each other or not? If there is a tendency for relative slip, then they will exert static friction on each other. And if there is no tendency for relative slip, then they will not exert any static friction on each other. So, in order to know that static friction acts or not between two bodies, we must know whether there is a tendency for slip or not. If there is a tendency for slip, then static friction will act. If there is no tendency for slip, static friction will not act. Now, the question is how to find whether there is relative tendency for relative slip or not. How do we determine whether there is a tendency for relative slip or not between the two bodies B1 and B2 in contact? For that, what we have to do, we assume the surfaces in contact to be frictionless. Okay, and then we let the remaining forces on the two bodies act as they are. Now what we do, in the absence of friction, that is frictionless surface we assume, and we let the remaining forces on two bodies B1 and B2 act as they are, and then using laws of motion we determine whether the slip takes place or not at the contact point when the surfaces have been made frictionless. In case after the surfaces have been made frictionless, there is no relative slips taking place still. This means there is no tendency for relative slip. And if in absence of friction there is relative slip taking place at these 2 points, then this means there is a tendency for slip. Okay. Now then what we do, we again restore the friction between two bodies. Now if in absence of friction there was no relative slip, that means there is no tendency for slip. So even if it is restore friction in this case, B2 and B1 will not exert any static friction on each other. But in case there is a tendency for slip, that is, if in absence of friction there was relative slip taking place at this point, then there is a tendency for slip. In this case, when we restore friction, then two bodies will exert static friction on each other, non-zero static friction, in direction opposite to the direction of slip in the absence of friction. Okay. So this is the rule for determining whether static friction will act or not between two bodies in contact and no relative slip taking place at the contact point. And no relative slip taking place at the contact point. Alright. So this is the rule. Alright. So if in absence of friction, there is no slip taking place, there is no tendency for slip. In that case, if we restore friction, then the two bodies will not exert any static friction on each other. If the surfaces have been made frictionless and there is actual slip taking place between B1 and B2, then there is a tendency for relative slip. In that case, when we restore friction, again make the surfaces in question rough, then B2 and B1 will exert static friction on each other in direction opposite to relative slip when the surfaces had been made frictionless. Okay. So by this rule we can determine whether static friction will act between two bodies or not. Okay. Now I'll take some examples to demonstrate this concept. I'll just take some examples, okay? See, first example is this. This is a fixed rough table, okay? This is a fixed rough table surface. This is a fixed rough table surface. A block of mass say 2 kg is lying on this surface. Okay. Let us take G to be 10 meter per second square. This table surface is horizontal, okay? 2 kg block is lying here. Suppose here the coefficient of static friction is say 0.6. Okay. Now this block is at rest on this fixed rough horizontal table surface. Now we have to determine whether the table will exert friction force on 2 kg or not. This we have to determine. Okay. So what we do first of all, we make this surface in question frictionless. Assume it to be no friction at all. Frictionless surface. Now what I do, I draw the free body of this 2 kg block and I show all the forces on 2 kg other than friction. So what are the forces on this 2 kg block? One is 2g weight. This surface exerts a normal force N on the block in upward direction. Okay. So when the surfaces have been made frictionless, only these two forces act on this. Now you can see that in the influence of these two forces, the body will not move at all. And will just cancel out the weight 2g, 20 Newton. So this block will still not slip over this surface when the surface has been made frictionless. So in this case, we will say that there is no tendency for relative slip. So when we restore friction again, then also friction will not act on this body due to the table. So in this case, static friction on block due to table surface will be 0. Okay, fine. Because there is no tendency for relative slip here. When I made this surface frictionless also, then also this 2 kg block will not slip over this surface because only 2g and n, these two vertical forces acting on this 2 kg block. It won't slip on this table surface. So there is no tendency for relative slip. So when I restore friction, this surface will not exert any friction on each other. Okay. Now one more thing. In this case, what is F max? F max is mu Sn. Mu s is 0.6. N is simply 20 Newton. This becomes how much? 12 Newton. So in this case, in order to prevent relative slip, friction can assume any value between 0 to 12 Newton. But in this case, as I have explained just now, amount of static friction on this block due to table surface will be 0. That is, the table surface will not exert any static friction force on this 2 kg block. So in this case, we will say that friction is present but is not being activated. It is not being used. Okay, we will say like this. In this case, we will say that friction is present but is not being used. Okay. See, whole sole objective of static friction is to prevent relative slip. That's all. It is only interested in preventing relative slip, static friction force. Okay. So it has only a single point objective, just to prevent relative slip between the two bodies in contact. For that, it can assume any value between 0 to mu Sn. So in this case, it sees that even if it does not act, then also there is no relative slip taking place between the two bodies. So friction will not act in this case. So we will say that friction is present but is not being activated. It is not being used. Okay. Just take an analogy. Suppose there is a police force. Okay. There is a contingent of police force, say 20 police personnel. They are only interested in assuming that there is no disturbance taking place in the society. Okay. So if they see that without firing itself, peace is maintained, they are happy. They won't fire at all. But if they see that if they don't fire, then there is going to be disturbance, so they fire in that case. So the aim of police person is just to prevent, is to maintain peace in the society. If it sees that without firing also, peace is maintained, they are happy. Their objective is being fulfilled. So why should they fire? Okay. So we can, from this analogy, we can understand. So whole sole objective of static friction is to prevent relative slip. So it's, in this case, it sees that even if it doesn't act, then also there is no relative slip. So it is happy, its objective is being fulfilled. So even when surface is made rough, this stable surface will not exert any static friction on this 2 kg block. Alright, this was the first example. Fine. I'll take the second example, okay? I'll take up another example, example 2. Example 2 is this. This is a fixed rough inclined surface. Fixed rough inclined surface. Fixed rough inclined surface. This makes some angle theta with the horizontal. Okay. A block of mass say 2 kg is at rest on this fixed rough inclined surface. Here coefficient of friction is some value, we have said 0.6. Some value I have taken over. Okay. On this 2 kg block is given to be at rest over this fixed rough inclined surface. Now we have to tell whether this rough surface will exert any static friction on this 2 kg block or not. This we have to tell. Okay. We have to tell whether this inclined surface will exert any static friction on 2 kg block or not. This we have to tell. So now what we have to do? First of all, we make the surface in question frictionless. No friction at all. Fine. Now I draw and I let remaining forces on 2 kg block act as it is. So in case the surface has been made frictionless, then I draw the free body of this 2 kg block. 2g, its weight, 20 Newton G10. This is the normal force on the block due to the inclined surface. These are the only two surfaces, only two forces, real forces. Now n will just be equal to mg cos theta, 2g cos theta, they cancel out. But component of 2g down the incline, that is 2g sin theta, there is an uncancelled force on this block down the incline. So in case this surface has been made frictionless, under the influence of the force 2g sin theta, this block will begin to slip over this rough surface, on this inclined surface. So what do you observe? In case of absence of friction, this 2 kg block will slip over this inclined surface. So in absence of friction, this 2 kg block will slip down the inclined surface. So here there is a tendency for relative slip. Now what I do, I restore friction again. I again make the surface in question frictionless. In this case, friction will act on the block due to the wedge incline, opposite to the direction of relative slip in absence of friction. In absence of friction, this was slipping down the incline with respect to inclined face. So in presence of friction, inclined surface will exert a static friction Fs on the 2 kg block up the inclined surface. So in this case, static friction is going to act, because it sees that if it is not present, then 2 kg block will slip over the inclined surface. So in order to prevent that slip, it is going to act on this block due to the inclined surface. So in this case, static friction on the block due to the inclined surface has a non-zero value. Okay, static friction on block due to the inclined surface has a non-zero value. Alright, fine. So in this example, there is a tendency for relative slip. So when we restore friction, we see that the inclined surface will exert a static friction on this block up the incline. Fine. Okay. Now rub this one. I take another example, example 3. Third example I take. Fine. The third example is this. This is a wedge, whose inclined surface makes an angle of theta with the horizontal. Mass of wedge is capital M, okay. Here it is a smooth horizontal surface. This is the rough inclined face of the wedge. Rough. Rough inclined surface of wedge. Okay. Here a block of mass M is placed. Now constant horizontal force F is being applied to the wedge. And this block does not slip over the wedge. Okay. This is the wedge W. This is the block P. Block has been denoted by P. Alright, fine. Now constant rightward horizontal force F is being applied to the wedge, and wedge and the block move together without any relative slip taking place between the block and the wedge. Okay, that is, they have a common acceleration A with respect to ground, say in rightward direction. Now question is, in this case, does the wedge exert any static friction on the block or not? That is the question. Question is whether the wedge exerts any static friction on the block or not. This we have to find out. This we have to tell. Okay. So now how do we decide that? That is the point to be discussed. Now it is being given that the wedge and block move together as a single unit under the influence of this force in rightward direction with a common acceleration A. So taking this wedge and block to be the system, if you write down the combined equation of motion of wedge plus block in rightward direction, what do you write? F is equal to m plus m into A. Okay, fine. I rub this, okay? So now we have to tell, first of all, it is given that the block doesn't slip over the wedge, okay? Now we have to tell whether the wedge and block exert any static friction on each other. See, answer is this. The wedge will exert a static friction on block provided if F is equal to m plus m into g tan theta, will imply that there is no static friction between the block and the wedge. That is what I am saying is that the wedge will exert a static friction on the block for if F satisfies certain restrictions. I will just state it first and then I explain it, okay? If F is equal to this much, then wedge will not exert any static friction on the block. In case F is different from this value, then the wedge will exert a non-zero static friction on the block. Okay, to be more precise, if F is more than this much, m plus m into g tan theta, in that case, the wedge will exert a non-zero static friction on the block down the incline. Fs will be non-zero and it will act on the block down the incline face. And this is the result which I am just stating. If F is less than m plus m g tan theta, implies will that Fs will again be non-zero. Now it will act up the incline face. This is the result. Now this we have to explain how we are getting this result. This we have to explain. Alright, fine. Now rubbing this. So first of all, what I do, I've assumed that the wedge and block have same acceleration A with respect to ground in rightward direction. This is the combined equation of motion of wedge plus block in rightward direction. F equal to m plus m into A. Now what I draw, we have to tell whether wedge exerts any static friction on the block or not. This we have to tell. Okay. So what I do, I make the surface in question frictionless. Okay, no friction at all. Now I draw the free body of this block with respect to wedge, assuming zero friction here, frictionless surface. So FBD of m with respect to capital M. Okay. So I have made the surface in question here frictionless. Okay. Now I draw the FBD of small m with respect to capital M. See, FBD if I want I can draw in ground frame also. But it's easier to explain if you use the wedge frame. So I am using the wedge frame to solve the question, okay? So I draw the free body of small m with respect to wedge, okay? Weight mg. The wedge will exert a normal force n on the block along the inclined face. Now this wedge is accelerating with respect to ground towards A. So wedge is a translating non-inertial reference frame. As seen from wedge, a pseudo force will act on the block in leftward direction, opposite to direction of vector A. And its magnitude will be ma. Okay. This is the inclined face. This is the angle theta. Now this angle is also theta, corresponding angles. Component of ma along the incline is how much? Ma cos theta. Component of pseudo force along the incline, ma cos theta up the incline. Component of mg down the incline is how much? mg sin theta. Okay, fine, all right. So now see, three cases arise. First case, as I repeatedly told just now, here I made the surface in question frictionless. Surface here has been made what? Frictionless. Surface has been made frictionless. So now what I will say in this case. First case is this: if ma cos theta minus mg sine theta is 0. What does that mean? Resultant of this along the incline and this down the incline is 0. That is, they cancel each other. What does that mean? This means that even when the surface has been made frictionless and this condition is being fulfilled, then this block will not slip over the inclined face of the wedge. So in this case, there is no slip between the block and the wedge. NS meaning no slip. NS between block P and wedge W. In this case, there is no slip between the block and wedge, even in absence of friction. Now, this means there is no tendency for relative slip between these two bodies. So when we restore friction again, then for this value of A, static friction on block due to wedge will be 0. So in this case, I will say that friction is present but is not being activated. Alright. Now MA cos theta minus mg sin theta is 0. This means if I cancel out M, what does it mean? A cos theta minus g sin theta is 0. A is equal to g sin theta by cos theta, that is A is equal to g tan theta. Now substitute this value of A here. F is equal to m plus m into g tan theta. So if F is equal to this much value, then this wedge will not exert any static friction on the block. Reason is that there is no tendency for relative slip when F has this value. Why is there no tendency for relative slip? Because in absence of friction also, if this much F is equal to this much and MA cos theta is just equal to mg sin theta, they will cancel each other. So on this smooth inclined face of wedge, the block will not slip over the wedge if F is equal to this much. So in this case, there is no tendency for relative slip. So even if we restore friction, friction will not act because its objective for no slip is being fulfilled. Okay. So in this case, first result has been fully explained. Alright. Now I take the second case. Suppose MA cos theta is more than mg sin theta. If MA cos theta minus mg sin theta is greater than 0, this means M cancels out. A is more than g tan theta. G sin theta by cos theta, g tan theta. What does this mean? This means that if we make the surface between block and wedge frictionless and this is more than this, the resultant of these two forces, MA cos theta and mg sin theta, will be up the incline. It is non-zero value up the incline. So in this case, in absence of friction, the block will slip over the wedge incline in upward direction. So in this case, there is a tendency for US, that is upward slip. There is a tendency for US, that is upward slip. That means what? That means that in case there is no friction between the block and the wedge in contact, then the block will slip up the wedge incline if A happens to be more than this value. So in this case, there is a tendency for upward slip meaning US. In this case, if we restore friction, in this case friction force will act on the block in direction opposite to the tendency for relative slip. So in this case, static friction on block due to wedge will be non-zero and will act down the incline. That is opposite to the direction of relative slip in absence of friction. Okay, in absence of friction, this will slip up. So when we restore friction, the wedge will exert a static friction on the block down the incline. Okay, now A is more than g tan theta. This means F will be more than m plus m into A, that is g tan theta. So if F exceeds this value, then static friction between block and wedge will be non-zero and its direction will be down the incline. Okay. And on third case, in case mg sin theta is more than ma cos theta, that is ma cos theta is less than mg sin theta. This means A is less than g tan theta. This means F is less than m plus m into g tan theta. Okay. In this case, what will happen? You can see mg sin theta exceeds ma cos theta. So in absence of friction here, this block will slip down the incline because mg sin theta exceeds ma cos theta. So in this case, in absence of friction, the block will have a tendency to slip down the wedge incline. So there is a tendency for downward slip in case the surface between block and wedge is made frictionless. So when we restore friction again, friction force will act on the block opposite to the direction of tendency for relative slip. So in this case, static friction on the block due to wedge will be non-zero and it will be directed up the wedge incline. Okay, fine. So by using this criteria, we can determine whether static friction between two given bodies will act or not if there is no relative slip taking place at the contact point. Alright, fine. This also I have fully explained. Alright. Before concluding this video, one thing I'd like to state. See, many students wrongly think that µs is always less than 1. No, it is not like that. Of course, in numericals, most of the time we encounter that µs and µk are both less than 1. But there is no hard and fast rule that µs and µk should also be less than 1. They can be any non-negative value. Okay, theoretically, µs can vary anywhere from 0 to infinity. And µk also can vary anywhere from 0 to infinity. But in numericals, most of the time µk and µs are given to be less than 1, 0.5, 0.6, 0.8, something like this. But there is no hard and fast rule, it can exceed 1 also. Okay. So this point should be noted down clearly. Okay. So now, this I have explained here. Alright. So in third video also I will take up a theoretical discussion on friction. Fine. And then I'll pass over to all the types of questions on kinetic friction. Okay. I'll close it here. Fine.